In this example, this design example, we're asked to show that the output resistance R out is equal to 50 ohms as seen by this load between terminals C and D. So we have a 50 ohm load, and what this 50 ohm load we'll see looking back at the output port of this interface circuit. So here's our interface. Circuit that it sees between terminals C and D a 50 ohm output resistance coming from the interface. At the same time, at the input interface, we want to have a 300 ohm input resistance seen between terminals A and B of this interface circuit. Meeting these two constraints produces match conditions at the input and output ports of the interface circuit. That is, Rin 300 ohms is matched with this 300 ohms of the source voltage, and R out is 50 ohms matching the 50 ohm load. To meet these two constraints, we chose an interface circuit that consists of two resistors formed as a L circuit configuration. We have chosen this L circuit configuration for the following reasons. The source must see a larger resistance of 300 ohms at the input port than the load sees at the output port of 50 ohms. This shows that the source should look into the large series resistor R1 while the load looks at the smaller parallel resistor R2. Now let's take a look at the input port where it has to equal 300 ohms. We see that R2 is in parallel with the 50, and this parallel combination will be in series with R1. In other words, R in is equal to R1 plus R2 in parallel with the 50 ohm resistor, which is equal to R1 plus R2 times 50 all over R2 plus 50. Now let's look at the output side of the interface circuit. R out, we can see that this 300 ohm will be in series with R1, and we note that we short out this voltage source to find the equivalent resistors across the terminals C and D when we look back here. So we see that R out is 300 plus R1 in parallel with R2. In other words, it's the product of those two, 300 plus R1 times R2 all over the sum of 300 plus R1 plus R2. So what we have is two equations, one here and here. This one is for R out, and this one is for R in. We can use MATLAB to help solve these problems, since solving them using a pencil and paper is a bit of a chore. At this point, we just need to encourage you to think about the problem in physical terms. So for example, if we simply set R2 to be 50 ohms, then the conditions at terminal C and D will be met at least approximately. So with R2 is equal to 50 ohms, the requirement at terminals A and B reduces to the following. Here we have R A and B is equal to R1 plus, and we say that, let's say R2 is 50, parallel with the 50 ohm load, which is equal to 300. In other words, R1 is equal to 275 ohms, while R2 is equal to 50 ohms. Now, how good is this solution? Well, these values yield an input and output resistance where RAB is equal to 300, and that's what's required. But let's look at RCD, which is basically 50 ohms in parallel with R2 is 50 ohms in parallel with 300 plus 275, and that's equal to 46 ohms. So this value is not exactly 50, but it's within 10% of the desired value. Since electric components can have tolerances in the 10% range, a design based on our first guess approximation may be adequate. Our first guess solution can also serve as a starting point for improving the design. The fact that RCD is 46 ohms tells us that R2 50 ohms is just a bit too low. Suppose we increase R2 to say 56 ohms, which is a standard value. Then at the output port we would have 300 ohms between the terminals A and B, while R1 is equal to 273. So the nearest standard value to this is R1 equal to 270 ohms. Based on this reasoning, where we have R2, we'll increase this to 56 ohms, then RAB is equal to R1 again, plus 50 in parallel with 56, which is equal to R1 plus 26.42, which is basically close to 300 ohms. That implies that R1 is equal to 273.58 ohms, and then the nearest standard value is R1 is equal to 270 ohms. Now, using R1 now to be 270 and R2 as 56, our second guess will be as follows. RAB is equal to 270 plus 50 in parallel with 56, which is equal to 270 plus 26.42, which is equal to 296.42 ohms. Pretty close to the 300 ohms that we have earlier. And then RCD is equal to 56 in parallel with 270 plus 300. Very similar to what we're doing earlier. So this is 56 in parallel with 270, and this yields 50.99 ohms. And both of these values here that we just calculated, here and here, is within 2% of the desired values. Thus, finding an approximate solution can serve as the first step in the design process. Finding that first step is often the most creative and challenging part of circuit design.